Hello everyone. Today we're going to see what are decision trees in machine learning techniques. Okay, so decision tree is a popular supervised learning algorithm which is used in machine learning for both classification and regression. So let us first see how decision tree actually looks like. So this is how a decision tree looks like. It's like a tree and there are branches emerging from a single branch. There are two other branches, there are three other branches that are emerging, and at the end there are the leaf nodes, what we call the leaf nodes. Here at the bottom you can see them. So this whole structure is what a decision tree looks like. So now we saw what a decision tree looks like, so let's understand what it exactly is. So if we go by the technical definition, so it's a supervised learning algorithm which is used for classification and regression. Now let's keep all these things aside and let us take a simple example to get an intuition of what a decision tree is. Okay, so for example, if I make a table like this, this is the gender column, this is the occupation column, and this is a suggestion column. So let's consider this table. We have the gender of the person and the occupation, whether the person is a student or a programmer, and here we have the list of the apps he or she installs. Okay, so for example, here the first one installs PUBG, second one GitHub, then third one WhatsApp, again GitHub, and then PUBG. Okay, what we can get when we see this table. Now when you see this table for the first time, what decision can you make in your mind when you look at the table for the first time? I can see that if the occupation of the person is student, so mostly there is a chance that he or she installs PUBG, and if the occupation is programmer, then mostly they install GitHub. Here programmer who is male installs WhatsApp. So in Python, if we want to express this in Python or any programming languages, we can express it in form of if or else statements, right? So for example, here we can express this particular scenario like if occupation is equal to student, then print PUBG. Else, if gender is equal to female, print GitHub. Else, print WhatsApp. So what does this mean? So if the occupation is student, okay, student, then we can see all the students are downloading PUBG. But if the gender is female and the occupation is programmer, then we print GitHub, as you can see in the table. And if the occupation is programmer and the gender is male, we print WhatsApp. So basically we can express this table as a nested if else conditional, right? So basically in layman terms, decision tree is nothing but a giant structure of nested if else conditions. So now you ask, if this is a nested if else condition, then how can we express it in the form of a decision tree? So let's express the same nested if else condition in the form of a decision tree. So how will it look like? So we can have our parent node as if occupation is student, if this is a yes, then it's PUBG, and if it's a no, then we ask another question, is gender female? Now if this is a yes, then we conclude that the app is GitHub, and if this is a no, we conclude that it is WhatsApp. Okay, so this particular structure is called a decision tree. So isn't it a good way to express the if else conditional, right? So basically how it takes place in machine learning algorithms. So as we did in this example, we first decided a good feature to split the data set. That was the occupation, right? So first we ask a question that if the occupation is a student, so it helps us classify the data set into two branches. So the first step in decision tree algorithm is to begin with your training data set, which would have some feature variables and classification or regression output. So we need to determine the best feature in the dataset to split the data on. Okay, so we split the data based on this feature, and then we split data into subsets that contain the correct values for this best feature. This splitting will define the node on the tree. All right, so this particular thing is the node. All right, so the features that we are splitting on are the nodes of our decision tree. So let us take this particular tree as an example. So basically this is the root node of our decision tree, and the subsequent node will be the decision node, and these ones will be our leaf nodes. Alright, these three are the leaf nodes. Now let's take this example in particular. So our first splitting point is this, and the second splitting point is this. So here we have two features. First is feature 1, which is saying if the value is less than 2.0, then we can label it as 1. If the value is greater than 2, then we will check the feature 2. If the feature 2 is less than 1.5, then we get 2. If the feature 2 is not less than 1.5, we get 3. So how do we represent this particular decision tree in the form of a graph? So let us make the x-axis as the feature 1 and the y-axis as feature 2. Now what was the first condition? The first condition was that feature 1 is less than 2. So here we have, for example, we have 2 over here. So we'll make a line that is parallel to the y-axis, which will show less than 2, right? So this part in our graph will be less than 2. So we make a line over here for the first root node, right? Then our next filtration is the feature 2 less than 1.5. So here the y-axis is for feature 2. For example, if 1.5 is somewhere over here, so we are filtering the condition which is less than 1.2. So we'll make a line that is parallel to x-axis over here, and we see that these portion in this graph will be less than 1.5, right? So now here we see if feature 1 is less than 2, then we can label it as 1. So if feature 1 is less than 1.2, so this particular area can be labeled as 1. Okay, now if the feature 1 is not less than 2, then we have another condition, that is feature 2 less than 1.5. So here in this area we will see that if the feature is less than 1.5, now in this area if we see, this part will be less than 1.5. Alright, so this part will get the label of 2, and the part which has the value of feature 2 more than 1.5, that is this part, will get the label 3. So this is how we are visualizing our decision tree. So what we are noticing here, that basically you can see this is the form of a hyperplane. So what we can conclude here is that decision trees use hyperplanes which run parallel to any one of the axis to cut your coordinate system into hypercuboids, we can say. Alright, so this is how basically a decision tree is represented. You can see that we first made a line which was parallel to y-axis, and then made a line which is parallel to x-axis. So further, if there are more nodes in the decision tree, we can keep going on, and we can make filtering conditions. So we can keep making lines that go parallel to the axis, and we'll come up with these decision boundaries. So these are called decision boundaries. Alright, so here we are basically classifying our data set based on this if-else condition, which are represented in form of a decision tree, and here we saw how it is represented in form of graphs. Alright, so what are the advantages of a decision tree? So it is an intuitive and easy to understand algorithm, right? It was so easy to understand and get an intuition of a decision tree, and its complexity is logarithmic, right? So the only disadvantage of the decision tree algorithm is overfitting. For example, if we keep making more and more decision boundaries, for example, if I keep making here, again here, so here we can come to a point when there is just one data point, and we are facing the problem of overfitting. So overfitting is a disadvantage, and if the algorithm is prone to errors for imbalanced data sets. So we need to make sure that our data set is balanced and proper, right? So this algorithm is also called the CART algorithm, that is classification and regression tree. Now the next important thing that comes in decision tree algorithm is entropy. So entropy is basically, in layman terms, you can consider entropy as the sort of impurity or uncertainty in the data set. So I can label it as impurity or uncertainty in the data set. So it basically tells how mixed or unpredictable the target variable is within a node. Okay, so just let us take an example. If I have a data set over here and I have another data set over here, so this data set is something like this. And this data set is something like this. Now you tell me that in both of this data set, in which data set can we guess whether a point will be of type X or type 0? Of course in this data set, right? Why? Because here the uncertainty is very less. In this data set the uncertainty is very less because we can see that maximum data points are of the type X. But here in the left hand side we can see that there are mixed number of X points and dot points. So here it will be more difficult, and hence we can say that the impurity here is more, right? So basically if impurity is more, impurity or uncertainty is more, then the entropy is more, right? So here we have less entropy, here we have more entropy, because here we can decide easily, but here we cannot decide easily whether it will be of type X or type 0. So what is the formula to calculate entropy? So entropy we can express as the summation of minus probability, where I we can take from 1 to n, right? So Pi is basically, for example in this example, we can take it as this X or 0. For example, in this particular example that we took, the entropy will be minus of Px into log of Px minus of P dot into log of P dot. That is basically the probability of a data point being from the X class, the total probability of X, and P dot is the total probability of this dot. Now we'll look at a very important visualization of entropy with the probability of a given feature, right? So if for example our data set can contain either a plus or a minus, so here on the x-axis we have, for example, the probability of a data point being from the plus, so the probability will range from 0 to 1. So on x-axis we have the probability, and on y-axis we will have the entropy, right? So now just assume that if the probability of P plus is 0, so all the points will be minus, right? So if it is a data set, all the points here at 0 will be minus. So if all the points are minus, the entropy or the uncertainty will also be 0, that is the lowest, right? Now as we go ahead, the probability keeps increasing, and for example if it comes at 0.5, so at 0.5 we will see that it is mixed, right? It will be a mixed combination of pluses and minuses. So since it will be mixed and the most uncertainty will be here, the entropy at 0.5 will be the highest, right? And again when the probability of P plus is 1, that means in our data set we are clear that all the data points will be of the type plus. So again here the entropy will be again 0. So basically our graph will look something like this. It will go upwards and it will reach its peak at 0.5, and then it will come downwards and again reach to 0 when the probability reaches 1, right? So here at 0, what type of data set we are having? It is a mixed type of data set with the highest impurity or uncertainty, right? So here highest uncertainty, and here we are having the lowest uncertainty. Here as well we are having the lowest uncertainty. The next very important thing in decision trees is information gain. So we saw that entropy is basically the impurity or the uncertainty in the data set. So through decision trees what we want to do is to reduce that impurity and classify our data set based on that. So a node should particularly reduce that entropy or the uncertainty to classify the data into two subsequent classes, right? So information gain basically measures that how much entropy of a data set decreases after a split or at a node. So for example, if we have a data set D and this particular node is classifying the data set into D yes or D no. So basically yes or no it is classifying. So what does it mean by information gain at this particular node? So it simply means that after classifying, the entropy of this data set is decreasing. So if here the points are all yes and here the points are all no, that means the information gain at this node is the highest because it is able to clearly classify the data sets into two clear classes. But this is a very hypothetical and ideal scenario. So it is not exactly that all the points here will be of yes or all the points here will be of the type no. So there is always some level of uncertainty, what we call entropy. So the lesser the entropy, the more the information gain. So more the impurity drops, more information gain happens. Okay, so the formula of information gain is, first we calculate the entropy of this particular node, that how much impurity is present at this particular node. Then we subtract the split times the entropy of each leaf node, that is D yes, and the split of D no times the entropy of P no. What is this over here, the split? So basically if we are taking the entropy of D yes, then it means that D yes, the number of data points in the data set with yes upon the total number of data points, right? So this is basically telling us the split of yes, and this is basically 1 minus the split of yes, which tells us the split of no. Okay, so what is the formula of information gain? So we are calculating the entropy of D and then we are subtracting from it the split of yes times entropy of yes minus the split of no times the entropy of no. So our target in decision tree algorithm is always to choose the feature, that will be the node, that gives us the best information gain. So that is about information gain. One more important thing here is that here, as we saw, that we represented decision tree in form of a graph, right? So the depth of the decision tree is a hyperparameter, right? So we have to cross validate on this depth as a parameter. So that depth is typically chosen using cross validation. So depth is a hyperparameter. We need to choose the proper depth that gives us the best results without overfitting. So that is all about our decision tree algorithm. I hope this lecture was very helpful and you understood all the concepts of decision trees. Thank you so much.